So, Taylor's error theorem. This is a bit of a mouthful. There are different versions of Taylor's error theorem, so you'll see different. If you're looking at another source, you might see it written slightly differently. There are different versions. There's the Lagrange form, the Cauchy form, etc. There are different ways this is stated, but it always says essentially the same thing. What you have is you have some function f of x, right? So you have this function, and you find a degree in power series for that function. So you find a degree in approximation, polynomial approximation for that function, using iterated derivatives, right? And A represents the center of that power series. Then what you want to do is you want to say, how bad could the error be, right, when we estimate f of x by Pn p sub n of x, right? So what we do is we want some formula that we can calculate, without knowing the true value of f of x. Can we have some formula that serves as an upper bound for the error in that calculation, right? So this is, if you wanted to think of this graphically, you could say, okay, I have A as the center of the series. I have this function f of x, and then I have this estimate, which we'll call Pn of x, right? Which is going to be perfect at A because you always started at the right point. And maybe it kind of follows it for a little while, but then it sort of diverges, right? The error grows typically as you get further from the center, right? But so then you have this value at x, and this particular x value that you want to calculate f at, right? So you have some x value. And what you're trying to do is you're trying to figure out how far apart can these be, right? That right there, that's the error. So this gap right there, that's the difference between f of x versus Pn of x at that point, at that particular x value, right? So another way to think of the upper bound is if you take, the true value minus the estimated value, you're trying to figure out, some quantity that's definitely greater, or at least greater than or equal to that difference, right? That's another way to think about the error. So now here, what's all in this formula, right? We have x is the input where you're trying to calculate your function, right? And A is the center of the power series. So that's where it kind of makes sense that the error would grow as x and A get further apart. If you think of how we build power series approximations graphically, right? N is the degree of the power series. So this n plus 1 factorial down there in the bottom kind of is nice, right? It's saying as n grows, typically the error will go down. You can't really grow down. I guess you can, but some things grow down. But the error will go down as n grows, right? Because factorials grow really quickly for most functions, right? That error will decrease as n increases. Now, the most cryptic term there in our estimate is m, right? What does m stand for? It stands for the max. M is for max, right? Max value of the n plus 1 derivative in absolute value, right, between x and a. So you're going to take your function, right? You take your function f, take n plus 1 derivatives, take its absolute value, graph that, right? So this is n plus 1 derivatives of f, and then look at that x value and that a value that you're trying to compute, and then what m is, right? So m then becomes whatever the max is on that interval. So at least the way I have it drawn here, that height right there would be your m, right? Because it's, at least the way I have it drawn here, that's your it's the tallest value on, I have it drawn where it's strictly decreasing on x to a, but it could be, maybe it's increasing and then the max would be at the right hand endpoint. Maybe it has a bump and the max is somewhere in the middle. It could really be anywhere between x and a, right? But so that's what m represents, right? So let's look at this now in a specific example. Let's apply this Taylor's error theorem. In particular, let's look at this example that we did in a previous video, right? Here's a way you could calculate an estimate for the cubed root of 1.1, right? So one way you could think of that is you take the function cubed root of 1 plus x, right? So this is our function f. And then you could plug x equal to 0.1 into the binomial series that represents that function. So in our example, we use the degree 3 approximation, right? And you could ask, how accurate does Taylor's error theorem promise that this approximation will be, right? So we need to get all of our information here. So probably the easiest one to pick out is n, right? N is 3. Why is n 3? Well, because n, remember, represents the degree of the approximation, right? So the fact that we're going up to x cubed means n is 3. We also want to talk about a. What is a? So a is 0. Why is a 0? Well, because this is the center of our series, right? If you look at these are just powers of x, right? There's no, it's not written as, x minus some other number. Like if it was x minus 1, x minus 1 squared, x minus 1 cubed, then it would be a equals 1. But it's not. There's nothing being subtracted from x. So you can think of it as just x minus 0, x minus 0 squared, x minus 0 cubed, right? So therefore our a is 0. Right. Okay. Then what else do we have? We have the function, right? We already found the function was this cubed root of 1 plus x. We also need m, right? We need this big M. So what is big M? Big M is going to be the max value on what interval? So it's between a and x. So between 0 and 0.1, right? Of the fourth derivative, because n plus 1, right, of f, right? That's how we get m. So let's do some derivatives here. We got to calculate this derivative to know what to use here, right? So I do a power rule, right? There's my first derivative, second derivative, subtract 1, right? Do the third derivative. So again, a power rule. And finally, the fourth derivative. So we get negative 80 over 81, 1 plus x, the negative 1/3. There we go. So there's our fourth derivative, right? So now what is the absolute value of the fourth derivative on the interval we're interested in? So we have our fourth derivative in absolute value. That's just going to get rid of that negative sign, at least on that interval, right? So what does this look like? This, if you think of this function on, what would the graph of this function be? Well, this function, it doesn't exist at x equals negative 1, right? Because you have division by 0 there. You could say when, and what does it do? It actually blows up to infinity there, right? Now, as x becomes really big, what is this function going to do? It's going to go to 0, right? Because it's a negative power of x plus 1, right? So those are the two asymptotes, right? The horizontal and vertical asymptotes. Then in between, it just sort of goes from one asymptote to the other. And where do we want this? We want this from x equals 0 to x equals 0.1. That's where we want to analyze this function. So if I have x equals 0, x equals 0.1, right? That means I'm looking at this interval. So what is m? M is going to be the height at the left-hand endpoint. So it's going to be 80 over 81, 1 plus 0 minus 11/3. Because that's where this fourth derivative is the biggest, is at the left-hand endpoint. So here, if I clean that up a little bit, right, what is the m? Well, it's just 80 over 81, right? Because that right-hand endpoint, that just is smaller, right? Anytime you go past that left-hand endpoint, all of these y values, they're all smaller than that very first one, right? So, and the 1 to the minus 11/3, that vanishes. That's just times 1, right? So there's our value of m. So now we actually have everything to plug into Taylor's error theorem, right? So plugging in all the pieces, what do we have? We have mx minus a to the n plus 1 over n plus 1 factorial, right? So I get 80 over 81 times x minus a, 0 0.1 minus, or sorry, 0 minus 0 0.1 to the 4 over 4 factorial. So then we get what? I have 80 over 81 here. I have times 4 factorial, 24 in the bottom, right? And then up top, I have 0 0.1 to the 4th, right? So 0.0001. We could reduce a little bit, right? So I have, let's see, between 24 and 80, I would have 4 as a common factor. And actually, sorry, 8, right? 8 is a common factor. So 10 and then 3. There we go. And now it's reduced as much as we can get it, right? So this is going to be 10 over 243, 0 0.001 is what this would be. And if we rewrite it as a fraction, we can even rewrite this as a fraction. So we'd have this 0 0.0001 is 1 over 10,000. You could cancel a 10 there, right? And if you cancel a 10, you get 243,000. There we go. There's our error bound. So Taylor's error theorem is promising us that the error on this is no worse than 1 over 243,000, right? So what does that mean? It means that the error, the error is less than this, right? The error is less than that amount, and in particular, the error is less than 1 over 100,000. I'm rounding down to the nearest power of 10. Why am I doing that? Well, because what does this mean? It means that if you take the true value of cube root 1.1 minus our estimated value, it means that that error is less than 1 over 100,000, right? So what that means is that the error is it means that these two values, they match out to the 100,000ths place, right? 100,000ths place, right? That if you subtract these, right, those digits would be the same, the true value and the estimated value. They would be the same. You'd get on the 10th place, the hundredths, thousandths, and 10,000ths, and even the 100,000ths place, right? And then after that, I don't know. After that, maybe then there's all kinds of error on these digits, right? I can't say that if you subtract those, I can't be sure that those are zeros anymore, right? So that's what this argues. It argues that because we got 1 over 100,000, Taylor's error theorem promises five places past the decimal of accuracy in this estimation, right? And if you look at it, this is pretty cool. It totally worked, right? So you do cube root of 1.1. If you do, say, a calculator value, right, this comes out to, let's grab it from up here, from our, where we had our estimate. This is our calculator value, right? So this was the calculator value, and versus this was our estimated value, right? Our degree 3 binomial series estimate was this was what we computed in a previous example here, right? This was our was this, right? This was our right? This was our estimate from the binomial series. And sure enough, you can see that it's correct to 1, 2, 3, 4, 5 places past the decimal, right? If you subtracted these, what would the error on these be, right? The error in their difference, right, would be what? 0 point, if you take their difference, you get 0.00000. You have 5 matching digits, and then our estimate had a 3 in the millionths place, right? Whereas the true had a 0 in the millionths place, right? So the actual error is something like 3 millionths, right? Which is less than 1/100,000, as Taylor's error theorem claimed. Right? So that's why we had 5 digits correct after the decimal place, because the error really wasn't there until the millionths place. There we go. So there's using Taylor's error theorem to analyze the error on a calculation, right? The true value versus the estimated value. Great. Thank you.